Friends, it's a great privilege for me to be giving this presidential address, my third one in the series. And in the first one, I had discussed some aspects of bacteria, the flocking behavior or cooperative behavior of the living or the active matter. In the second one, I had looked at bacterial heat engine. And today I bring you two stories from my lab, which I have put under the general theme of Science Without Borders to bring out interdisciplinarity and the interaction with other disciplines to look at the problem with some new perspective. So this is something which all of us know, that Science Without Borders or interdisciplinarity, as you would call, or cross-discipline, it is something which we all realize that it is now an essential aspect of science, because complex contemporary problems may not be amenable to single discipline knowledge, and we have seen that discoveries are more likely on the boundaries between fields, where perspective, concepts and tools can bring new insights. So we have seen, for example, the influence of big data science on many disciplines, which expand their horizon, discovery of new materials, and so many fields which have really benefited by bringing the perspectives of different areas and different experts on these problems. This is an interesting paper I had seen few years back, and I thought it may be relevant to see. It's a very interesting statistics they collected in 2015, looking at the influence of interdisciplinarity, how has it impacted. So on the left side, there is something where the degree of interdisciplinarity has been a factor in seeing how effective these publications are. They have a measure of how they measure this interdisciplinarity, but on the right side is they have data to show that the publications which have more of interdisciplinarity have long-lasting value, and it really increases with time. So there are various measures. Those who are keen to know how they are measured, this paper I would refer this. And the second one which it quotes in 2015, they have looked at again how the publications from different countries have looked at this aspect of interdisciplinarity, again measured by the references from different disciplines to quantify this aspect. And it's interesting to see that India really is top on this, that 13% of the publications really come from India, which have this interdisciplinary character. These numbers, of course, need not be taken very literally, but it goes on to show that there is a trend in this, and we should all be seeing where this cross-discipline interaction can really bring new perspective on the issues we are handling. So I thought in this 35 minutes, I will just look at two examples, though in my abstract I have put 3 examples to bring out. I don't think I'll have time, but something which we have been looking at, a very old problem in a way, it is century old, many centuries old, how the glass devitrifies. So this is something which has been there, but really we don't understand even now. And in recent times, we have used machine learning in this problem, and this is something, a beginning where many things are happening in physics using this tool. And the second one is something new to me very much, and this is the example where we have learned from the earthquakes community to look at what kind of statistics these events have, and we now see that almost everything what they see in earthquakes we can simulate in our experiments in the lab on a very small scale. And if you scale the length and time appropriately between earthquakes and lab experiment, they beautifully map onto each other. but it gives us another handle to look at this very complex problem of earthquakes in the context of this flow of soft matter. And the third one, which I thought I'll say, but I may not have time, where we have used the concepts in fiber optics and combined it with nanoscience to really make very cheap and efficient biosensors and chemical sensors. And this couldn't have been possible if I was not talking to people from fiber optics and biology. So this is something again thought I would say, but I may not have time. So this is the first story I'll just tell you as this is unfolding in the lab. So the student who is really deeply involved is Divya, and along these experiments are done in Professor Rajesh Ganpati's lab in JNC. And here this is a movie which is speeded up 10,000 times. These are colloidal particles of about 1 micron size, and here the advantage is that you can have this colloidal glass, the particles are arranged completely in a glassy form, and how they rearrange, this is without any applied stress. So the point is you can really image in time and space, spatial resolution, to look at each equivalent of an atom, what is happening. And this is something which is still not understood in the literature, why the glasses which are metastable phase, they can crystallize over a period of time. For example, there are naturally occurring examples which I thought would be interesting this audience. We have this obsidian rock from this is formed by cooling of the lava, and it has been seen that over long time scale, not the time scale of our time, but over 500,000 or 250,000, this obsidian, this crystallizes. So this glass becomes crystal and these white patches are seen. And this is something happens over very large time scale, geological time scale, but also on hundreds of years, and sometimes if you have a bad manufactured glass, you will also see over 20 to 30 years glasses become very opaque or translucent. That is because the crystallization is happening inside, which is scattering light. So for example, this is the devitrification of opal glass, the white patches, and this is again devitrified Roman glass over hundreds of years. And this is still a big mystery, how this transformation occurs. Because in a liquid you know that atoms can move and they can form a crystalline state, and you can understand from nucleation theory. But this is not obvious when it is a solid. Why should it really have the freedom for atoms to move and crystallize? So there are many places where you would wish to avoid devitrification. It's not a virtue you would like to avoid. For example, in nuclear waste, nuclear waste is contained in the glassy matrix, and because they want to contain it, and if it becomes crystalline over time, there is a large probability of leakage of this nuclear waste. This is something which has to be avoided. And in many drugs, they are cast in amorphous form, which are more soluble, and they would like to avoid crystallization as a function of with time, because it really hinders their solubility and bioavailability in their use. And there are other examples of biomolecule storage, where again the crystallization is not something preferred. So this is just a summary of what is known so far, and this problem has been done in computer simulation. There are very few areas, but I just tell you two key results what have come out. So it has been seen in recent computer simulations that if you look at atoms or these particles, you look at where they are forming crystals and where the particles are mobile. And what they have seen is that the fraction of crystallites in these glasses, they increase smoothly with time. So as the time progresses, this can be months, this can be years, then you have more and more crystal by slight reshuffling of the atoms. And this, what it happens is, where this red are the mobile particles allow, and the white are the ones which are glassy, which are not shown, but in this neighborhood the crystallites grow. So the crystallites grow by shuffling of atoms, and this is a slow shuffling, and this is how the crystals form. But there is another mechanism which has been seen, which is quite interesting, that if your glasses are very mature, what has been seen, that the number of crystals increase in burst. So there are avalanches which happen with time, at some time, huge rearrangement occurs, then everything becomes silent, and so on. So it goes in avalanches. So there are two routes, one is the slow shuffling, other is the avalanches. And this is what recent computer simulations have shown. But there is no way to know if the crystallization would occur and where will it occur in a glass. So no understanding of that exists, and this is where we have used machine learning to see if we can predict if the glass will form and where will it form, if at all there is a tendency. And this is something which I'll just like to present. So these experiments are done with colloidal particles, and they form a three-dimensional glass, which means the particles are arranged in a completely random fashion, which you can quantify. And this glass is watched as a function of time over 68, 70 hours or even 6 days in some cases, and every second is recorded what is happening to each particle. So you have the whole story recorded, and we know that we can really reverse the movie and see why the crystallization occurred in those events, in those places. And we have now a understanding what really is happening and where machine learning could be useful. So I'll just give you that example. So here, this is the way there are measures to define if the particles are in a crystalline environment. There is a very rigorous way to do this, which is called bond orientational order. I don't intend to make explanation of this because this is quite standard. And what we see is over 68 hours in this colloidal glass, you will see this red particle, the pink particles, which have become crystalline, starting from small number to large number. And this is really in one two-dimensional plane in a crystal, but we have all the images in 3 dimensions. Now, in these systems, we do see 2 routes to crystallize. One, this is the avalanche like what I mentioned, where you see the number of crystals really go in spurts, and we have a complete understanding of how starting with you have very small crystals and how they grow through the avalanche route. So there is an avalanche route which really takes the particles from glassy state to the crystalline state. Another route which we see again in these systems is the smooth route, where the number of crystals grow smoothly with time, and again we know how at each time the particles shuffle little bit, and we have quantified all these motions in these 2 different types of crystallization. But this is just at a glance. I don't know if you can catch. Oh, it's not. So here you would see in the avalanche, suddenly you will see large number of reshuffles with these yellow things happening, and then everything will be quiet. Whereas here, which is quantified in those diagrams, you will see that it's a very smooth operation of the particles, which really rearrange. So this is something which we can follow as a function of time. Now, here the question came, which I asked, how do we know the crystallization would occur, if at all, and in what parts of the system crystallization will occur? So this is where this recent advances in machine learning have helped us. So I don't think I'll have the time, but I'll give you the gist of what is done in these fields. So what is done is, that in this simulation, this is a simulation 2016, they look at these particles and they identify using machine learning, which I will just tell you, whether the particles so-called are soft or hard. Soft means that they can undergo rearrangement, hard means they retain their position. If the computer can be taught how to identify soft and hard particles right in the beginning of the experiment, just with 100 or 1000 images, then we have seen a very strong correlation when the crystallization occurs with this hard or soft particle. So the machine learning is used by looking at the structure around each particle, identify them as hard or soft. This is where the machine learning goes in, and then we see that the crystallization occurs where there are soft particles. So right in 1 hour we know what will happen after 5 days, and it exactly happens where the soft particles are. So this is the tool which we have used, which is called support vector machine. Essentially it's a very simple science. So what you have to do is you have to classify, you have to define something which computer can recognize. So computer has to be taught what exactly you are looking at. Supposing you want to classify, for example, how good are the peach fruits, whether it is ripe and good to eat or it is rotten and not good to eat. So you can define by colors. So you can do this experiment for, let's say, 20 to 30 peaches. Computer knows what is good to eat, what is not good to eat. So it's just a one-dimensional problem, and then it will define that if the next peach comes and you define its color, whether it will be good to eat or bad to eat. It's a very simple problem. You don't need machine learning for that, but it's just an example. But now if you complicate it, supposing you have peaches and plum and they have a large and small size, so your dimensionality is high. So you have to know whether it's a good peach or a bad plum and so on. Again, you can define a two-dimensional space, and you can have a situation where you will have good things to eat, like yellow peaches with large size is good to eat, and these are not good to eat, other things. But now you cannot divide. The computer will not know whether if the next one comes, where to put it in this space, because there is no easy demarcation of these two things. So this is just a two-dimensional thing, but it can be more complicated. So what a support vector machine does, it converts this into this higher dimensional space, and then it turns out with this higher dimensional space, as you will see, there will be a dividing line between the good ones and the bad ones, and when the next example comes, the support vector machine will tell you whether it is a good thing to eat or bad thing to eat. Now this is in two dimension. The thing to define can be many more quantities, and this is where we use in our problem about the structure. So we quantify the structure with their descriptors. This is a 40-dimensional space, and support vector machine algorithm really divides the particles, whether they are hard or soft, depending on how they move in the first half an hour to 1 hour. After that, it can identify all other particles with that knowledge. And it is interesting to see that what we found in this example, that soft and crystalline particles completely overlap. So in the first half an hour, we defined soft and hard. Computer learned it from the structural information, and after 68 hours, this is exactly where the crystallization occurred, and this is decorrelated with the hard particles. So this is something where the dynamics is embedded in the structure, which something was hidden unless we use these tools of machine learning to really understand. So this is, I thought, one example where hard and soft definition of the particles using machine learning has helped us to look at this devitrification problem. So in this example, what we see is the two routes to crystallization. That is something which was known in computer simulation, but we can exactly identify the moves. and more importantly, the structure is really hiding all the dynamics that will happen. So it really has all the information, only thing you need to quantify. So using soft and hard particle concept, we exactly know where the crystallization will occur. And this is something not explored before, and we think that this language or the tools of machine learning could be useful in many examples. Second example, which I just show you as a interaction with the people in geophysics and actually mathematicians, is this example of earthquakes, which really came when I heard a talk by A.K.Sood, who was visiting IISc, and he's an applied mathematician and he works on complex systems. So his talk gave me an idea that whatever he was showing for earthquakes, we realized that we are seeing in some of the experiments, and we got to talk to him and learn what earthquake community does in these examples, in this data analysis, statistics, and this is what we are trying to do. So I'll just in next few minutes I'll point out that. Since some of you may not be familiar with this term soft matter, let me take 30 seconds to that. Soft matter is all around us. So whatever examples you see in daily life, be it the shampoo, be it the toothpaste, be it the jelly, and be it the coffee powder, be it the paint, milk, all are examples of soft matter where the reorganization or the arrangement is happening on a very large length scale. This is not on an atomic scale. So these things are extremely soft, and they flow in a very interesting manner. The reason they flow is that there is a very strong correlation between the structure of how the particles are arranged and their flow. So they influence each other, the structure and flow, and it gives rise to many phenomena which have industrial application. For example, shear thickening, shear thinning, and so on. What it means is that if you take Newtonian fluid like water, and if you shear it, you will have the viscosity, which is simply a ratio of stress over strain rate. This is what we know in high school. And the viscosity of water does not change if you keep on stirring in a mixie in the kitchen. But the same thing does not hold good when you put something in water, for example cornstarch solution, and as a function of stirring, properties will change. And this is what is called non-Newtonian fluid, where you can have shear thickening or shear thinning depending on the material. So there are many examples in daily life which use this. For example, you would like shear thinning in some cases, for example in shampoo, but you would not like shear thickening in some example, which is what happens. And this is all, I will not like go, but the whole point is the relaxation of particles in these systems happens over millisecond time scale. And when you are shearing at the same time scale, there is an intense interaction between the structure and the flow, which is not possible in water. Water, the atoms rearrange over picosecond time scale. In such a fast time scale, you can never shear. So that is why this soft matter is a very wonderful class of systems where you have this non-equilibrium flows, non-equilibrium effects come in the picture. For example, on this tube, you can see that you can take a balloon and you can fill with water. Nothing will happen if you shoot a pin on this. But the same thing you do, same balloon, you put water but little bit of cornstarch, which you can buy in the market, and now you puncture it, and you will now see that it will not float the way it flowed. It flowed like a huge thick gel. And this is where the shear thickening has happened by the act of probing, punching. And this is something used in many possibilities. One example is this body armor. So what people have seen, that body armors, you can take Kevlar sheets and you can put 10 of them and it will stop the bullet. That is what our policemen wear. But what they are trying to see, can you reduce the number of these Kevlar sheets and still have the same purpose? So they put the shear thickening liquid between the two sheets of Kevlar, and that acts, because the act of bullet really makes it hard at that time and it repelled. So it's the same 2 Kevlar sheets instead of 10, but with a fluid which is the cornstarch or the silica particles in between, and that is how the shear thickening can be used for this body armors. So this is one example, but there are other examples where shear thickening can be a real nuisance, and that is a billion-dollar industry. So what people have seen is that if you take, this is how the cement is pumped by machines into the building exercise. This is, you must have seen many places in the city, especially high-rise. But what happens is, in the act of pumping, the cement slurry becomes shear thickened and it blocks. And there are huge accidents reported in the literature where the pumping has made the cement slurry thick and it has caused problem. So there is a whole lot of research in this field where different additives and different protocols are used not to have shear thickening. So the 2 examples are extreme. In one case you can use shear thickening to your advantage. Another example is where shear thickening is a nuisance and it is huge cost to avoid it. So there are 2 sides of this phenomena, and you need to understand that if you need to make any progress. So this example is a limited story, but just to tell you where the surprises are. So what we do is, this material is really what you have in daily life. For example, the honey will flow, though it's viscous, but this toothpaste will not flow, it will remain solid. So what it says is that this soft matter like toothpaste has a yield stress. It needs certain stress to make it flow. This is something known for 100 years. It's something very, very well established. So what happens is, you need to apply some minimum stress before it starts flowing. That is how you must have seen. You have to pinch your toothpaste with some amount of force before the toothpaste comes out. Now what happens, what we ask is, supposing you don't apply that much stress, very little stress that it is not flowing, but ask anything happens. So till now people believe nothing will happen if you do very small stress. But the example which I will quote you is exactly contrary to that. So what we do is, we have soap solution. This is soap molecules. You put them in a water with 39-40% weight, and they form some pneumatic type of behavior, and they form these domains. These domains of pneumatic one really are jammed in this material, and the material does not flow till you apply a certain stress. And this stress is about 20 Pascal, and this is the usual what people know. So what we are doing now in the next 5 to 7 minutes, we will ask what happens if you make the material shear in a very small stress below this value. What is really happening? Because this is something which has been unexplored in the last 100 years. So what we found, that we start measuring the shear rate versus the time at a very small stress of 2 Pascal, much below 20 Pascal, which is the yield stress. And we found that nothing was happening in the beginning, but then at about 1000 to 500, 1500 seconds, a huge burst came, the material flowed, and then it again became extremely silent. And this is something which is not unique to this material, I will show you. So if you look at this data, how the acceleration of the plate or velocity of the plate or the shear rate, it looks with time, it is somewhat like the earthquake. This is the real earthquake data. Here the ground acceleration is plotted versus time, and this is where the main earthquake occurred. So the question we are asking is, the statistics of this earthquake which have been studied in the last more than 100 years, does it have any similarity to what we are doing on this scale, and is there a lesson to be learned? And this is something, the earthquake is the literature is the one which we learned from this applied mathematician and how they look at it. So we found that this earthquake-like phenomena occurs in a window between very small value, nothing happens, but little more, all these things are happening. So the material is reorganizing. So the viscosity, this is what it means is that it's a large change in the viscosity, large reorganization. So this reorganization, does it have any message? So these are various experiments to show that it's robust, and this is where we went to the literature and learned little bit on earthquake. So my knowledge is only 1-2 year old, which could be pretty dangerous. But we learned what are the kind of things they have looked at, and this is what people know, that what is the frequency of occurrence of these earthquakes. So for example, earthquakes are given by Richter scale. So if you know in UK, which is not an earthquake prone area, if earthquake between 3.7 and 4.6, if it occurs every year, this law tells you that if you increase 1 order of magnitude of earthquake, it will occur 1 in 10 years. So it gives you some idea. This is just an approximate number, but it's a good scaling law. So it's very important to see how the energy is released in these earthquake events. So this is the earthquake data, and people would like to know what is the frequency of earthquake events as it comes to the main earthquake and after that. Because people would like to know how aftershocks are occurring, and this goes down as 1 over T raised power alpha, and this alpha is the Omri exponent. Similarly, this energy exponent is another exponent, and which people know what is the value in this earthquakes. And this is what people have done for many systems. This is the decay of activity Omri law. I said 1 over T. The exponent is 1, and people have seen over this earthquake, huge number of earthquakes, Gutenberg-Richter law, 1 over E behavior with some exponent, and this is the time interval between earthquake events. And what is the time interval? This is also a power law. So there is a huge effort in the literature to see what can be understood from these power laws. So I will just be brief here to tell you that the kind of data we have, we apply the similar tools of what earthquake community does and see whether it has some similarity. And I'll tell you what more we can do, which they may not be able to do. So we look at this data. This is the main earthquake event light, and this is the pre and this is the aftershock. After that, everything becomes silent in this example, but in other examples, it also has many more earthquakes. So we look at this Omri law from this data, and it exactly follows 1 over T behavior, which means the events after the main event, they decrease as a function of time in this 1 over time, which is what this data shows. We use the wavelet transform, which I will not go over. Again, a very useful construct, and wavelet transform exactly tells you what is happening. And there are much more richer data here, which is called log time periodicity and so on, which is all happening in the experiments we are showing. Without going into detail, we see that this Gutenberg-Richter law is obeyed, 1 over E raised to power 1.5, which is exactly what earthquake literature has. Then we have more experiments to verify this, and the waiting time distribution also is a slope of 1.6, which is what earthquake events have seen between 1.2 and 1.9. And this is again need to understand what is exactly happening. So the strength of this physics experiment comes in the following. We have everything happening on a tabletop, which means in this rheometer things are flowing. We have the advantage of looking inside the material when the event is happening, which cannot be done obviously in earthquakes. So what we do is we set up a microscope along with this, and when these events are happening, we look inside in this by imaging. And what we see is actually a huge reorganization efforts are going on inside it, which is exactly what happens, how these plates move, when how the fault propagates in earthquakes, how this reorganization occurs. And this is the kind of images which change drastically, and there is a huge change when this event occurred, which I did not point out, but when there was no stress, nothing really happened. So now we can quantify this without going into detail. We can see the length scales from the structure factor where these events are happening, and again use what is done in computer science called computational information density. It tells you how much image you can compress, which is what you use in lab, JPEG file, and that also has information which we have extracted. So I think I will probably not give all the detail. This is not unique to soap solution in high concentration. This is happening, for example, if you take laponite clay, put them in water, they form a glassy state, and there also you will see huge reorganization events happening in this. You can have many more quakes than one of them, and again they follow the well-known statistics. So I think I'll just close this talk to say that we can scale our experiments with the earthquakes, because you have to realize that earthquakes occur over 100 kilometers. We are having experiments over few micron. So there is a length scale difference which is 10 to the power 10. And there is a time scale difference because earthquakes happen over months and years. Here the phenomena is happening over tens of seconds. So we have the time scale also scaled up. If you scale these two, we have realized that the stress which is released in earthquakes and the rupture velocity, they exactly map to this laboratory system. So it means that we have an opportunity to learn something hopefully about this earthquakes by looking at this physics experiment. So I think let me summarize this part and close this to see that it's an opportunity in the soft matter community to understand this reorganization and look at this phenomena which has some similarities, not a lot of similarities on earthquakes. I think I will close this talk, I will not mention this. This is a platform where we have combined fiber optics and nanoscience and make the sensors. So I think with this, let me close this talk. I just show the last slide that this was an attempt in this address to take some examples from our lab and see what we have learned from other disciplines to make some contributions to those problems. Thank you very much.
Thanks, we are just exactly on time. We will now break for tea. All the fellows are requested to go up front for the photograph, and we will assemble here at 11 o'clock. All young associates also are requested to join the photograph session. And also I like to mention that all the books which INSA has produced will be available for purchase at 50% of the cost for next 3 days. To kindly use this opportunity. Thank you so much.